Welcome again, everyone. So we're going to continue with the next talk from this session, and the talk is going to be delivered by Juanita Duque-Rosero. Juanita is a PhD candidate at Dartmouth College. She has a Master's of Science from Colorado State University, and she did her undergraduate studies at the University of Los Andes in Colombia. Her research is focused on computational number theory. Thank you very much, Juanita, for being here to give us this talk, and you may begin.
Thank you, and thanks to both you and Catalina for the invitation. I'm very happy to be here. I wish we could be in Costa Rica right now because I'm in very snowy New Hampshire. I don't know if you can see all the snow from my window. So it'd be great to be there. Hopefully one day we can do it. Great. So today I'm going to talk about work in progress with John Voigt. And it's about enumerating triangular modular curves of low genus. So first, I'm just going to give you a really short outline of how this talk is going to go. I'm going to give you an idea of what our main result is. And then we're going to go through the motivation. Why would you like to study these curves? How do you define them? And then how do you study the genus and have an algorithm for enumerating all the curves of a given genus. Okay, so to start, I just want to give you an idea of where are we going to. So at the end of the talk, hopefully you will have a better idea of what all these objects are. But what we do in this work is just to enumerate all of certain curves that we call triangular modular curves that have monodromy PSL2 or PGLQ, and we enumerate the ones that have genus 0 and 1 in particular. Great, but before we get to this theorem, I want to start with the motivation. And thanks, David, for your lovely talk, and also for convincing us that modular curves are a very essential part of mathematics and number theory, right? So a modular curve is a Riemann surface constructed as you can think it as the compactification of a quotient of the upper half plane by the action of a congruent subgroup, right? So we take subgroups of SL2Z in this case, and we act on the upper half plane by just taking a matrix A, B, C, D, and then multiplying it by complex number whose imaginary part is bigger than 0. And then we get AZ plus B over ZZ plus Z, right? So we have matrices acting on the upper half plane, and then we consider all the orbits of this action. These form a Riemann surface, and it's a modular curve. Here is a great picture of the fundamental domain of gamma 0, 5, one of these congruent subgroups. And that's how the action looks like, yeah, the fundamental domain looks like. Great. Why do we, part of the reasons why do we want to study modular curves is because they parameterize our loved elliptic curves, right? If you take certain congruent subgroups here, you get a modular space for elliptic curves with certain properties, right? So if you, for example, take the congruent subgroup gamma n, so that's matrices that are congruent to the identity mod n. This parameterizes elliptic curves with a basis for the full n torsion. So knowing rational points on this kind of curves is knowing elliptic curves that have a basis for the full n torsion. You can do the same for gamma 1. So matrices that are congruent to that are upper triangular mod n and have ones in the diagonal, and they give us elliptic curves with a point of order n, so a little bit less than full n torsion, but it's still pretty good. And then gamma 0 gives us elliptic curves with a cyclic isogeny of degree n. So it's clear that we have that these congruent subgroups are contained in each other. So we get maps from for the curves, right? We get some maps here, and maybe we could study, a good idea will be to study these covers to understand all these curves for these particular congruent subgroups. Okay, so a natural question that you can ask is, okay, these curves parameterize elliptic curves with certain properties. So when are there infinitely many elliptic curves that have a given property? So you can ask, when are there infinitely many curves with an isogeny of degree 7? And we know that for a curve to have infinitely many rational points, the genus have to be, so genus is 0 or 1, right? So maybe studying the curves, the modular curves that have genus 0 and 1 is very important. And that was done by Fricken in 1922. So he actually classified all the curves, the classical modular curves, X naughts. I have the result for here, but there are similar results for X1s. That have genus 0, 1, and he actually did all up to genus 7, I think. So we know how many, we know if when there are infinitely many elliptic curves, for example, with an isogeny here, with a cyclic isogeny. And then all this work is very important for theorems like Mazur's theorem, classifying the torsion of the Mordell-Bell group of an elliptic curve. So thanks, David, again, for convincing us that Mazur's theorem was important. Great. So again, the story is classical modular curves. We understand them very well right now. We know which ones have genus 0 and 1, and they tell us information about elliptic curves. So we are going to try to generalize this picture. And to do that, we are going to talk about triangle groups. So here is a small definition, and I'm just going to say that the triangle group delta of ABC is just a group that is presented like this. So it has 3 generators, and the generators to the A, to the B, and to the C are 1, and then the product of all of them is also 1. So the picture that you should have in mind with this presentation is you choose a triangle. The triangle can live in the hyperbolic space, just as I have here. So you choose a triangle. Let's say that this is our triangle, this pink triangle that we have here. It's hyperbolic, and that's why we have curvy lines. And then we start thinking about the isometries of this triangle. So we can do some reflections, right? We can, as we are showing here, we can map the reflect over the y-axis, and we get this triangle here. Or we can reflect over this side. I guess I'm missing one triangle here, reflecting over that side. And then what these generators are doing is it's counting the isometries that are orientation preserving. So if we rotate once, we are going to change the orientation. So maybe we can reflect again. And that's our delta A, for example, is reflecting once and then reflecting twice to make it orientation preserving. So it's nothing weird, although the definition is kind of weird once you first see it. And then what we are doing, how do you do this, is we are choosing a triangle with angles pi over A, pi over B, and pi over C. That's how the ABC are related to the triangle group. Yep. And here I drew a triangle in the hyperbolic plane because those are the only ones that we are going to care about. So we're going to say that a triangle group is hyperbolic if and only if this quantity that depends on ABC is less than 1. Is less than 0, sorry. And here is a really nice picture from Escher of angels and demons that comes from thinking about hyperbolic triangles in the upper plane scene. So this makes sense. I just want to convince you that it makes sense by computing pi over a plus pi over b plus pi over c. So this is just the sum of the angles of the triangle. We know that in regular geometry, like the Euclidean geometry, this sum of the angles should be pi. So 1 over a plus 1 over b plus 1 over c is 1. So this quantity that we have here is 0. If this quantity is bigger than 0, actually, you get a triangle that lives on the sphere. And then being less than 0 means that your triangle lives in the hyperbolic plane. Okay, so now we have our actor, and then we have this triangle group. This is going to be the analogous to our matrices SL2Z. And now we want to have this triangle group acting on the upper half plane. So how do we do this? So this is going to be the definition of triangular modular curves. And what we can do is that thanks to Takeuchi, we know that there is an embedding of triangle groups delta of ABC into PSL2R. So matrices, 2 by 2 matrices with coefficients on R up to multiplication by a scalar matrices. So this embedding can be made explicitly, but don't pay much attention to these formulas. I just wanted to convince you that you can actually see this embedding. And then, so using this embedding, we can have a triangle group, delta of ABC, acting on the upper half plane, right? We send it to matrices with coefficients in R, and then we have those matrices act on the upper half plane, just as we did in regular modular curves. So now we can study the orbits of this action, and it turns out that if you study the action of the triangle group delta of ABC on the upper half plane, you get a complex Riemann or one orbifold of genus 0. And we say that that's our triangular modular curve. So this is our definition of a triangular modular curve. And why do we care about studying these curves? So modular curves were really important to understand elliptic curves. These curves are actually important to understand other geometric objects, and these are called hypergeometric abelian varieties. So these varieties are just Jacobians of generalized Legendre curves that look like this. So it's an upgrade, kind of a generalization from elliptic curves. Now they look like this, and we are studying the Jacobians of these abelian varieties. So here ABC can be given explicitly in terms of little a, little b, and little c. So that's kind of the analogous that we have with modular curves. And we can ask the same questions. Can we put some level structure that tells us a little bit more about our Jacobian varieties? And then can we study different congruence of groups of these triangle groups? So the answer is yes to all of those questions. So first, we are going to focus on level structure. So to understand level structure, there is a little subtlety, and is that we cannot think about rational numbers. We actually have to think about level structure of prime ideals that live in this field E. And yeah, don't pay much attention to the definition of E. This just comes, actually, this is the trace field of the matrices that embedded our triangle group in PSL2R. So we study these primes P, frag P, that live in this number field here. Note that since all the generators are cosines of these kind of angles, we actually can rewrite this as a sum of est roots of unities. So these fields all live in cyclotomic fields. So they are easier to understand. Okay, so now we can define level structure using this prime ideal, P. So it turns out that there is a homomorphism that goes from the triangle group to PSL2 of the residue field of our B prime here, F. So this is just a finite field, and we can find a homomorphism that goes from the triangle group to this PSL2 of this finite field. And we can understand it explicitly. So we are going to let the triangle group with level structure P be the kernel of this homomorphism. And once we define this, we can define our triangular modular curves with level structure. And these are given by Clark and Boyd in 2019. So they take a hyperbolic triple and they take a prime just as I described before. And they further assume that P does not divide to ABC. There are some generalizations where you can have P divide into ABC. But for simplicity, I'm doing this. So then there exists a G-Galois belly map from this curve to P1, where the ramification indices are actually A, B, and C, and where the Galois group is given by matrices, just as we have here. And PSL and PGL just depends on the splitting behavior of your prime. So these are our triangular modular curves with level structure. And we can understand them better because they are belly maps. So they behave really nicely. And since they are belly maps, computing the genus is really easy. They are Galois belly maps. So the ramification is the same everywhere. And we can compute the genus, and it's just given by this formula. So analogously, we can have a very similar definition when n is any ideal. It doesn't have to be prime. But for but we're going to focus on primes just to make our computations easier. Okay, so we know the genus really easy. And then we can enumerate all the curves with a given genus. Turns out that there are only finitely many. But maybe let's focus on just congruent subgroups. So again, we have now level structure. Now we can think about congruent subgroups. So to think about congruent subgroups, you want to take that homomorphism that we defined before. That was just, and then remember that the triangular modular curve with level structure was just defined by the kernel. And then we can define the subgroups that live in PSL as just matrices, as we did before. So H0 was upper triangular matrices. And then this is kind of the gamma 0 that we were studying before. And this is the gamma 1 that we were studying before. Okay. But these live in PSL2. So we can take pre-images, and now our congruent subgroups actually live in the triangle group. So since they live in the triangle group, we can again play the same game and define the curves that we want. So we have the action of delta 0 of any ideal on the upper half plane, and that's going to be our triangular modular curve x0. Here, sorry, I'm missing an ABC. This all depends on the ABC you pick, and here too. And so we can define these curves just as we did before. And then just as the case of classical modular curves, we have maps that go like this. And these maps, I'm just writing them here because they turn out to be very important whenever we are doing algorithms to enumerate all the ones that all these curves that have low genus. We studied this cover a lot because as we saw, this is genus 1, so genus 0, sorry. So it's a P1. So we studied this cover a lot. And then we study this cover a lot to understand the genus of the X1s. Yep. So that's the definition of our curves. And then in the last 10 minutes I have, I just want to talk about the algorithm on how would you compute the genus of these curves, and then how would you enumerate all the curves of a given genus. So to study the genus, we are going to focus on the X naughts. And from knowing the genus of the X naughts, knowing the genus of the X1s is fairly straightforward. So the big lemma here, which is kind of a group theory lemma, and yeah, it's a cute lemma, is that the genus of X naught is given by this formula. So I wrote it here like this because it looks like Riemann-Hurwitz, and that's what we are doing. We are just using Riemann-Hurwitz to compute the genus. So what we have is a cover of X naught of A, B, C, comma P, a cover of P1, and this cover turns out to have degree Q plus 1. So we have -2 times the degree, and then we just need to understand the ramification of this cover. And it turns out that this cover really wants to be totally ramified. Every point wants to have as much ramification as it can, but there are some divisibility issues. So it has as few fixed points as it can have, and then all the other orbits have length A or B or C. So that's what this case means. Depending on the divisibility conditions, you have just 1, 0, or 2 fixed points. And then everything else lives in an orbit of length S. Okay, so we can understand the genus of these curves. We can just solve for G and understand the genus. And moreover, we get a bound for the genus. It turns out that the genus is bigger than, well, a lower bound for the genus given by this. And remember that this was our special number that told us that the triple was hyperbolic. So that's going to play a role into our computations. So let me rewrite that inequality here, same as before. And now for any hyperbolic triple, it turns out that this quantity that we have in our formula is bigger than 1/42. And that's not hard to see. It's like you know that A, B, and C are bigger than 2, and then you just find kind of the minimum triple that you can plug in that is hyperbolic. It turns out to be 237. So you plug in 237 and you get 1/42. So what does that mean? It means that if you fix your genus, G naught, and then you solve for the genus from this inequality, you have a bound for Q. So you have a bound for how big our Galois group is. And then once you have a bound for Q, you have a bound for A, B, and C. So what this means is that for a fixed genus, there are finally many curves, X naught of A, B, C with level structure P of genus G naught. So now we know that there are finally many, and we would like to enumerate. That's what we do. We enumerate all the triangular modular curves that look like that using the genus formula and some bounds that we get. And we found that there are exactly 47 curves of genus 0, and then exactly 131 curves of genus 1. And now that we have these curves and we know that they come from belly maps, the next step will be to understand the rational points on these curves. And that can tell us some information about our hypergeometric abelian varieties. So in the last 5 minutes that I have, I just want to give you an idea on how the algorithm runs. Just a quick glance at the algorithm. So what you want is all modular curves X naught of ABC that have genus G naught, right? And Galois group PSL or PGL of a finite field. So what you do is you have a bound for Q. So you loop over all possible powers of primes that are smaller than this bound. And then you find all the possible triples. For each Q, you find all the possible triples that you can have for a triangular modular curve. And remember that our lemma was about divisibility. And the only conditions of divisibility is that your triples divide Q minus 1, Q, or Q plus 1. This is one of them. So you actually have finitely many options for your triples because you have been fixing Q. And then for each triple, you can check that there is another bound that comes also from Riemann-Hurwitz, just to make sure that you're being as efficient as possible. And then if this passes, then you can compute the genus using the corollary that we had before. And if you find the genus, you add it to our list of low genus. Okay. So for genus 0, this algorithm runs in, I think, 10 minutes. So it's pretty efficient. For genus 1, it runs in an hour. So that's been really great. I've run it for genus 2 and 3. So we also have those lists. And that takes a little bit longer. But in principle, it works for enumerating any like the curves for any genus you want. And from knowing the ones of genus, the ones for X0, you can find all the ones for X1, because remember that there is a cover from X0 to X1. So the X1s that have low genus really need to cover X0s that also have low genus. So you have finally many options for the X1s too. And then to finish, I just want to give you a list of these triples and primes that have genus 0. Remember that here I am lying to you. The level structure is given by a prime above a rational prime, but it doesn't depend. It actually doesn't depend on what prime we choose. So that's why I'm putting. I'm drawing. I'm listing the rational primes here. Yeah, so those are all the curves X0 of ABC, prime ideal of genus 0. Great, thank you for your attention.
Thank you very much, Juanita, for the wonderful talk. Are there any questions for Juanita?
Thank you for the talk. It was very, very interesting. I have so my understanding is that there's also like a theory of modular forms on triangle groups. And so my question is then, is there any kind of L function and some kind of modularity kind of expectation in this setting as well?
That's a great question. I actually don't know the answer. Yeah. I think there should be, but yeah, I don't want to say something wrong. Sorry.
Are there any other questions? Okay, I have a question, Juanita. One is, I think, what does it mean when you define the triangle group at the beginning of your talk and you gave this presentation, but you had that A, B, or C could be integers or either infinity. What do that relations mean, or one of the relations would mean if one of these A, B, or C is infinity?
Yeah, thanks for asking. So yeah, we just say that delta infinity to the infinity is just 1.
Okay.
It's bad notation, but
okay.
Yeah, it works. I mean, you can allow these triangles to have angle 0. In the upper half plane is just kind of triangles that look like this. They don't look like that much like triangles, but they work. And that's something that we also do.
And the other question I had is, maybe you mentioned this and I missed it, I don't know. Can these triangular modular curves be, the regular modular curves in some instances for some values of A, B, and C, or? Yeah,
that's another great question. Thank you for asking. Actually, yes. So if you do 2, 3, infinity, we know that PSL2Z can be generated by an element of order 2 and 3, right? So these give you classical modular curves. And then when you put a prime, you also have level of structure. So
I see. Thank you. Yeah. Are there any other questions? Okay, well, if not, then let's thank Juanita again. All right. Yes, Ronald.
Yes, thank you, Adrian. Actually, once again, I want to thank to the organizers of this thematic session, to Adrian and Catalina. Thank you very much. This was a very, very nice thematic session. I really enjoy it. This is not my area, but I really enjoy the speakers, the way you organize it. I am very proud, actually, and I am pleased the way you did it. I hope the participants as well did the same. Okay, thank you so much from the organizing committee. I really appreciate it. Thank you.
Thank you also for your work, Ronald, and for the opportunity to have this thematic session. Okay, well, the next talk would be in about 28 minutes. That's going to be the plenary talk by Angela Robinson, and Catalina is going to be the chair of that session. I believe that session or that talk has a different Zoom meeting, right? If I'm not mistaken.
That's right. That's right. Actually, yes. Thank you. Actually, that's a very good advice. Yes, that's another link. It's another Zoom link. Everybody, well, that one is also in global UCR for those of you that are interested. Actually, probably all the people in this thematic session are interested in the plenary talk.
I have the link, I believe. Let me see.
Maybe I can share it in the chat as well.
Yes,
right
yes,
now.
yes, you do it. I don't want to be responsible if I give a wrong link.
You can also find it under conferences in the global UCR.
Yeah, that's true. Here it is. Yes, thank you, Adrian, for reminding me. Thanks once again.
Okay, well then, once again, Juanita, I think David's no longer here. He had to teach, but thank you everyone for coming. Thank you for the talk, Juanita. And well, let's hope this is just the first time and that we can continue, having these thematic sessions, and let's hope that that number theory can grow not just in Costa Rica, but in Central America and in Latin America as well. Thank you, everyone, and I hope to see you again in less than half an hour for our plenary talk. Thank you, and good afternoon.
Thank you.
Good afternoon, everybody. Bye.